Should I also write here?
Yeah, you also need to write some. They count this for lunchbox.
Okay. So. Thank you very much. And so maybe I start with recalling something last time. So let X omega be a symplectic manifold, but I often only consider closed case closed symplectic manifold. And let L be a closed embedded Lagrangian submanifold. And maybe equipped with spin structure. Maybe equipped with spin structure. Yeah. And then from here, actually, I can associate some algebraic gadget, so that is filtered infinity algebra. So here I have this cohomology of X, lambda 0. Maybe I also recall what it is. And bunch of operations here. So this is filtered infinity algebra. So here, this lambda 0. Last time maybe I wrote lambda 0 no, but lambda no 0 or something. So this one is, by definition, certain formal sum, like E. E is just some formal variable. So E to the mu and T to the lambda. So they are both are formal variables. And maybe AI is in certain coefficient ring. But today I may consider only complex numbers. In general, we can consider coefficient ring as an algebra over field of characteristic 0. But anyway, today I only consider complex numbers. And mu integer and lambda be a real number. And then I assume that if there are infinite many terms, then this, mu I lambda I. So mu I lambda I. And if there are infinite many terms, then lambda I diverges to plus infinity. So this sort of goes here. And so sometimes it may be easier to consider some variant of these things, namely just suppress this variable E. So this one is, here actually, this one is, like this, and this one is the same thing, but without this E. Numbers and mu I integers and lambda I is actually, yeah. Mu, no mu. So only lambda I. Yes. So that if there are infinite many terms, this lambda I diverges to infinity. So this is actually a graded ring by putting the degree of E equal to 2 in our case, because in our case, actually, the Lagrangian manifold has spin structure. In particular, it is oriented manifold, so therefore, all the Maslow's indices are even. So in this case, actually, we will consider E of degree 2. But anyway, so if you suppress this, then this is no grading here. But later, maybe I may introduce some grading in some cases, but okay. So this is lambda 0. And then this one contains lambda no plus, or this lambda r plus. So here, this is the same thing, but this lambda I is actually strictly positive, right? So this one also same thing, but lambda I is strictly positive. So here I assume non-negative, but okay.
So is the A infinity algebra is H at all, right?
Infinity algebra? Yes. Ah, sorry. So this is sorry. Thank you very much. Yeah. Sorry. Okay. So here I consider the following. So over lambda 0, maybe lambda 0 minus 0, we consider something like, yeah, we call additive variation on it, mapping it to R negative. So namely, if you have some element here, AI, T lambda I, and then all the exponents are non-negative, so we may take just the minimum of this exponent, so lambda I, so that AI is non-zero, certainly. And then we have a map. So this is a variation. And this lambda plus minus 0 is just this VT inverse of R positive, right? And this is so and also this lambda plus in lambda 0. This is certainly ideal, but this is actually maximal ideal. Because the difference is only the constant term, so therefore if you mod out by lambda 0 by lambda plus, then this one is actually isomorphic complex numbers, so therefore it's a maximal ideal. And actually this is a unique maximal ideal, so therefore it's actually a local ring. And then we can also consider the following. So here we have this lambda 0, and then the field of fractions of this lambda 0 is nothing but lambda, namely this is actually sum AI T lambda I, so that AI is in complex number, and lambda I is just a real number, so that if there are infinite many terms, this lambda I diverges to infinity. So this one certainly is bigger than this, but this one is actually a field fraction of this ring. And there is a fact. Maybe this one I may just I didn't really mention this last time. But in this case, this lambda, lambda. So here actually I only consider complex numbers. This is actually algebraically closed. So maybe we gave a proof of this in one of our papers, but this fact is quite well known in algebra, and so maybe it's a standard fact there. And maybe if you want to know the reference, maybe I can tell you the reference. Okay, so this is for this version, not on this version. This version has this E, and then this lambda knob is not really a field, but this one without E, we can show that it's actually closed. So here I don't have any E here. Okay. So how we define this? So take beta from second relative cohomology of this, and then consider the moduli space of border stable map of representing class beta, so that we have k plus 1 map points on the boundary. So this is a moduli of border stable maps of genus 0 and connected boundary, and with k plus 1 boundary map point. So namely, maybe simplest case is somehow I just have a disk with k plus 1 map points on the boundary, and then map to manifold X with Lagrangian boundary conditions. So therefore, the picture may be something like this, and then there are a bunch of points here, and then I require that this map represent class beta, right? And if you want to know more complicated pictures, then certainly there may be other kind of pictures here, or maybe here, maybe you may have some sphere bubble here, or maybe here you have other one, and then maybe you also have some sphere bubble here, and then a bunch of map points on this. But anyway, so in this case, maybe I have Z0 and Z1 and Z2 and Z3 and so on. And anyway, the boundary is connected by this assumption. So therefore, this boundary actually has an orientation as a boundary of these components. And so now I put the numbering of map points which respects this cyclic ordering. And so in our book, actually, sometimes we put here main here. It means the numbering actually respects this cyclic order. But I only consider such a thing, so therefore I just remove here. And then this one is mapped to, I don't know, maybe I cannot draw so many things, but maybe here I have another disk. I don't know, another disk here, and then maybe sphere is attached here, or maybe some other disk somewhere, and so on, right? Something like this. And then you have some map points on the boundary of this. And then the total relative homology class is equal to beta. Okay, so you may consider such a thing. And then we have evaluation map from this space to this Lagrangian manifold L. Just sending this, maybe I just give it a name here, U. So here maybe U, and then sigma d sigma, and Z0, Z1, Zk. They are point of the boundary, map to XL. So I don't put any constraint at this moment. So take a class. It's mapped to U of Zi. Right? I just take a value of U at ith map point. So this is evaluation map. And then we have this following picture. So mk plus 1 beta here. And then we consider some sort of pullback and push out. So if you have such a correspondence, you have some operation from here to here. So from here to here. So for instance, if I use a differential forms, then maybe I have this omega dot of L, tensor K goes to omega dot of L. So namely, I just put back. So here I have say C1 that are CK. And then here I just put back this one and then take exterior product. And then we just take a push forward of this. And this one is the element here. Right? So this one, I may just denote by m k beta of C1 ck. Okay? And so if beta is constant, beta is just a trivial. And k is equal to 0 or 1, then actually m of k plus 1 of beta, so this is either this m1 beta equal to 0 or m2 beta equal to 0, and they are actually empty because you have a constant map from the disk, the constant map, and then the automorphism group of such object, such a constant map with one map point on the boundary or 2 points on the boundary, the automorphic group is infinite. Right? So therefore, there is no stable one. So in this case, we don't really use this. And so we define this M1, M0, beta equal to 0 case, then I just put it 0. And M1, beta equal to 0 thing is actually, now I use this differential form, then this is actually exterior derivative. So this is a kind of special case, and this special case, we just put M0, 0 is 0, and M1, 0 is equal to D, exterior derivative. And so other cases, actually, we use this as a definition of this MK beta operations. And then finally, I put this MK is a sum of MK beta with some t to the power area of beta, beta omega or something. So this one, yeah, you have infinite many classes beta, so that this one is non-empty. Then this could be infinite sum. Then the convergence is become an issue. But if you put this extra things, and then by Gromov compactness, if this area is bounded, then only finite many class beta appear, right? So if you consider this modular space so that this thing is bounded by some constant. And then there is only finite many classes beta, so that this one is non-empty. So therefore, this one converges in t-adic sense, namely, with respect to this. So this variation gives a certain topology on this. Like if the power of t going to infinity, then it converges to 0. So anyway, so this one somehow, if we put this one is actually well defined. So this one is well defined, so kind of Gromov compactness. Implies this one is well defined. I mean, certainly we have to make sense of these operations, but that is actually kind of virtual technique. And then each of them actually defined by using virtual technique. And then this infinite sum makes sense because of Gromov compactness. Okay. So, we have this omega dot here, and maybe tensor this lambda 0, and over there we have this MK things, and then this becomes so-called filtered infinity algebra, namely, if you consider. Sorry, maybe I need to put certain sign here. So here I have xi1, xi minus 1, and here xi, xi plus k2 minus 1, and xi k or something. So if you consider such an infinite sum, then this is equal to 0, right? So first we can cook up filtered infinity algebra, and then it is actually a algebraic process. So actually we can also introduce some infinity structure here. So this one is actually what we call canonical model or minimal model. So what is this? So this one is a cohomology of this guy with respect to this M10. So M10, this one. And so this algebraic process is the following. So you have some infinity algebra, and then you can take a cohomology of this one with respect to M10, and then this infinity algebra structure actually induces infinity algebra structure on the cohomology with respect to this. So this is one algebraic statement. So therefore, in the statement I said that we have these things. I didn't write canonical here, but anyway, this is a one consequence. And today I will speak about the torus fibers. Torus fibers in compact toric manifold. In that case, actually, we can cook up this thing rather directly, without really working on the whole differential forms. We can actually come to this directly. So that is one thing I may have to say. Okay, so I have to I have to keep this maybe somewhere. Okay. So this is one thing. And then next I want to recall the notion of weak Mallow-Cartan element. So this is just an algebra. So let's consider C dot and this MK. Filter to infinity algebra. And then take B from here. So actually we take a element of degree 1 in a sense. But degree 1, yes, degree 1 in a sense. And then we consider this following thing. So I take EB. So this E is nothing to do with E for the Novikov ring. This is, yeah, just a similar. I mean, yeah, this is E as you know. But this one is actually a bit strange because this one is actually we define in this way. So namely, this one is just a sum of B to it. So it doesn't look like an exponential, but this is in some senses, it's exponential. And later I also use usually exponential, so therefore I don't know how to really distinguish it. But yeah, if I have infinity algebra and then take element B from C1 from here, and then if I write E to the power B, and then this always means this. And then like this. And then I have to say the following. So B is a solution of Mallow-Cartan equation if this one is equal to, Mallow-Cartan element, better to say this, because the equation is an B is a Mallow-Cartan element if this one is equal to 0. And this is what we call Mallow-Cartan equation in this infinity algebras. And there is a notion of unit. So there is a notion of unit of filter to infinity algebra. So we denote by E. So this one is the following. So this MK and something and E here and something. This one is always 0 unless K is equal to 2. And K equal to 2, it behaves like a multiplicative unit. And here I take, I think, degree X, yes, and M2 XE. So if you have such an element, then we call E the unit of filter to infinity algebra. And in this construction, actually the unit on the ordinary cohomology, namely the class represented by a constant function 1, is a unit in there. Okay. So this is a unit of filter to infinity algebra. And then I want to continue this discussion, so B is called a weak Morakawa element if this M star dB is proportional to the unit. So this is proportional to the unit. So namely, this is equal to some A times this E. And A is from this lambda 0. But in fact, it's actually lambda plus. Yes. So, okay. So this is the definition of weak Morakawa element. And more precisely, in order to make sense of this infinite sum, at the beginning we consider only B with positive power in T, no constant term. And then this infinite sum always makes sense. Later, after the idea by Cho, actually we can also consider the constant term. Maybe that I may explain later. But anyway, so this is one. And then we have this Morakawa set Morakawa element. So this one is L. Maybe this. This is a B weak Morakawa element. And then we have MC weak M tilde going to lambda plus. So this is what we call potential function. Namely, this thing, right? So M star EB is equal to potential function L of B times this unit. Okay? So this is the value of the potential function. And there is so-called gauge equivalence. I don't know, probably last time I didn't really tell you the gauge equivalence. So I don't know, maybe I can speak of it maybe in supplementary talk. But anyway, so this one actually descends to the kind of modular space of weak Morakawa element. So namely, this one is MC weak tilde of L modulo gauge equivalence. And then actually, this one actually descends from here to here. So this one we also like potential function of L. By abuse of notation, actually I use the same thing. So I think last time I just give you the definition of weak Morakawa element as this potential function. And today I want to compute part of it in the special case of toric manifolds. Okay. So this is okay. And then one more thing is we can deform infinity structure by as follows. So you have C1 ck. So we have this MK operation, and then the family of this MK operation. Then if we have B, then we can also consider the following. So you just put arbitrary number B before Xi1 or between Xi and Xi plus 1. And even after Ck. Yes. And then actually the fact is this MKB is also a filtered infinity structure. This also gives you a filtered infinity algebra structure. So up to here, actually, I don't really use any property of B, just maybe B, maybe degree 1 or something. That's enough. But if B is a weak Maurer-Cartan element, then some good thing happens. That is actually this M1B is equal to 0. So why such a thing is true? So this is actually come from here. So I consider this M1 of psi. Then this one may not be equal to 0, but maybe we have M01 tensor psi plus minus 1 to the xc plus 1, or xc minus 1, and xc minus 1 of M2 of psi tensor M01. This is equal to 0. So if we have this relation, yeah, you just consider the case that this k is equal to 1. So this k is equal to k1 plus k2 minus 1. Okay. So then you have this. Certainly, if M01 vanishes, then M1 square is equal to 0. But if even M01 is non-zero, if it is proportional to the unit. So if it is proportional to the unit, then we have this. And so maybe here I wrote x, but maybe xc, maybe I just write here xc, and this is xc, and this is xc, and this is xc. Sorry. This is xc. So if it is a unit, then this one is xc, and this one is minus 1 to the degree of xc times xc, right? But here you have minus 1 to the degree xc minus 1, so therefore in total you have minus of xc. So therefore this is plus xc and this is minus xc, therefore they cancel out, right? So this M01, maybe, sorry, I can just write B here, because everything holds for any infinity structure. So if this one is proportional to the unit, namely B is a weak Maurer-Cartan element, then this M1B is equal to 0, right? So therefore this. Maybe I can also tell you one more thing. So probably last time maybe I didn't really say this. So I take M1, and here I have M2 and xc1 tensor xc2. Okay? And then this one is equal to, no, this one plus, M1 xc1 tensor xc2 plus minus 1 to the power xc1 minus 1 of M2 and xc1 tensor M1 xc2 plus M3 of M01 tensor xc1 tensor xc2 plus minus 1 to xc1 minus 1 of M3 of xc1 tensor M01 tensor xc2 plus -1 to the C1 plus C2. -1, so it doesn't really matter. So therefore, I just put it this way. And then M3 of C1 tensor C2 tensor M01. This is equal to 0, right? So I just write the case k is equal to 2. And then I have this equation. So I have 6 terms. And in general, we have these 3 terms. But if this is proportional to the unit, right? If it is proportional to the unit, this is equal to A times E, and this is equal to A times E, and this is A times E. It's a multilinear map, so that A is just to put outside. And then this thing. So if in this case the K is equal to 3, right? M3. So therefore, if you put E here, then all these 3 terms die. So therefore, you have kind of likeness rule, right? So therefore, I put here B here, then I can put B everywhere. Sorry, I put B everywhere. So B here, B here, B here, B here, and B here, B here. Okay.
But the notion of units depends on E?
No. So notion of unit. So certainly. So notion of unit. Certainly, at the beginning, I have a notion of unit, right? And then, if you consider this thing, then actually, if E is one of the entry, then only M2 contribute. So if you insert B, then you may have more, right? So another is M1. Yeah. So maybe you may ask whether this M1 BE is equal to 0 or not. And this is only non-trivial things, but then this one is actually M1E plus M2 BE plus -1 to the degree B minus 1. No. Sorry. And M2 of EB. Yes. Plus so on. But all of them die because M3, M4, if E is one of the entries, then all die. So we have only these things. But this one is equal to 0 by the definition of unit. And these two actually cancel out because this one is equal to B, but this one is equal to -1 to this B of E, so B of B. Right? But we assume that this one is degree 1, or maybe order degree. So therefore, this one is equal to -P, so therefore they actually. So anyway, so you don't have these terms. So therefore, you have a following thing. So if B, so here I just write maybe 2 things, and then M1B and M2B satisfy kind of likeness rule, right? I don't know this. Is this? I don't know this. I don't know this. This spelling is. So this fact I will use later. So if B is a weak Manhattan element, M1B gives you differential, and also M1B and M2B satisfy these things. In particular, if M1B C1 and M1B C2 both vanishes, and then this C1 tensor C2, the M2 of C1 C2 also killed by M1B. Right? So that I will use later. I think this may be most of the thing I have to tell. Okay, so the notion of unit, and then notion of weak Maltner-Cartan element, and then if you have a weak Maltner-Cartan element, then you have a M1b becomes a differential, and this is some sort of bottommost type Floer complex. This gives you bottommost type Floer complex, and then so this is actually two consequence, and also this to satisfy kind of Leibniz rule. Okay. So now I think, maybe later I have to also discuss bulk documentation, but maybe it may be too much at this moment. So therefore, I just stop here and then come to toric examples. Okay. So today I start talking about this Lagrangian theory of torus fibers in compact. Compactness may not be really important. Compact Kähler toric manifold. Okay, so this is a topic I want to discuss today and probably also next time. Okay, so first of all, maybe I have to recall something about toric manifold. And I don't know whether I am a good appropriate person to explain this. Maybe some other people may be better, but anyway, so I will try this. So, okay, so let X be a complex manifold. And which contains the complex tori as an open dense subset. And here it's a complex tori, and so here you have certainly the action of complex torus here just by multiplication. And then if this action actually extends to the action on X, then we call it toric manifold, right? So X is a complex manifold, and this one actually extends to this action. So namely, it is actually this torus equivariant compactification of this complex torus, then we call it toric manifolds. And there are some description of this. So there is so-called fun picture. Or maybe originally it is actually defined by using fund. So people may use n. So n is a lattice. I mean, n is actually a free abelian group of rank n. And maybe it may be better to think of it as a space of continuous homomorphism from S1 to T. So T is actually here. T is actually a n-dimensional torus. I think this is okay, right? So continuous homomorphism from S1 to T, or maybe just a homomorphism as Lie groups from S1 to T. And then, what is fun? Fun is a collection of rational polyhedral convex form. So namely, so they actually, yeah. So maybe so you may have a vector like a A1, AN. Sorry. Maybe I have to say this. So here N. So fun is actually sorry. I have to consider the real vector space. This fun is a collection of rational polyhedral convex cones in NR with certain property. So namely, so if you have K, anything P in N, then you can consider something like sum of Ti and AP, AI, I is 1 to P, so the Ti or negative. And then certainly it is actually a cone. And so let's suppose that, so this is a cone, but we assume that we don't have any line, right? So we assume that, so it doesn't contain any line. Okay, so maybe this strongly or strictly convex cones. So if we, so this polyhedral thing, actually you have several integral vectors and then span something, and then you have this set, and then assume that this strictly convex is that it doesn't contain lines. So such a thing actually is rational polyhedral convex cones, and such that so the intersection of any members, any two members, sorry, is this really correct? Any two members, yes, or any members is a face of each cone. So intersection is and belongs to the collection. So this is a collection of such a convex cones, and then you take an intersection, and then intersection is also a member over here, and also the intersection is actually a face of each member, right? So this is actually the one. I don't know. I have to keep it. And then, if we have a fun, I don't know how fun, what is the notation of fun? But then from fun, after you can construct some toric manifold, toric variety. So basically, maybe. I don't really explain the whole thing, but anyway, so this fun actually gives you toric variety. And then, what else? So this one is actually compact. So this condition is actually equivalent to the condition that this fun actually is a union of this fun covers whole NR, and it is non-singular if so any member any top dimensional member of the fund is actually a span, is actually spanned by some V1 to the Vn, A1 to An. This is actually a basis, integral basis of the lattice. Not the vector space, but this lattice. So integral of the integral lattice. Okay. So I don't really use fun picture so much, but at some moment actually I may have to use some terminology. So therefore I just like this. And toric manifolds, even manifold case, actually toric manifold may not be scalar. But if it is scalar, actually scalar case, actually we have another description by polyhedral polytope, convex polytope. So in that case, actually you have X, and certainly you have a complex manifold. Therefore, so here you have a complex factorization here, right? But here is a scalar metric here, or maybe scalar metric G and G gives you scalar metric here. And then we have a momentum map. So here we have X to this real algebra of the torus. So certainly, this group is non-compact. So therefore, I have to take its maximum compact subgroup. And if necessary, we can take average of the metric, and then we have a compact torus invariant scalar metric. And so in this case, actually, we have a momentum map. So this is going to the real algebra of the torus. Start. Okay. And so here I introduced this lattice, and here I introduced the dual lattice. So M is actually the home of NZ, and this one we can also consider as a set of continuous homomorphisms from T to S1. So this is actually a set of one-parameter subgroups, and this is a set of characters. And so they are dual each other. And so this one is in fact, yes. So because this one, if you consider generator of this is actually a generator is actually element in Lie algebra, and this is a character, so therefore it gives you a dual of this. So therefore this one is in fact this R. And here, the image, so I have a momentum map. For some reason, I use this pi, so this is very strange, but this is a momentum map for this torus action. So here, actually, I have a torus action here, and then momentum map for the torus action. And so then we get the image. So P is the image of this. And so then this is actually T and Gilman-Sternberg's convexity theorem. This one is actually a convex polytope. And in this case, actually, it was well studied by Zeldan, so therefore there is a polytope. Or maybe we may also call it momentum polytope. And this is expressed as follows. So P is a convex polytope. So therefore, it is defined by a collection of affine inequalities. So in fact, P, so P is actually written as follows. So U is in this MR, so that there are some integral affine functions. I don't know, this is, affine functions, Lj of U. So this Lj is a affine function, so that the linear part is actually integral with integral coefficient. And so here I take a Vi, Vj, and here U. So this one is from M side, and this is N side, and minus lambda j. So, okay. So polyhedral, this convex polytope is defined by collection of affine inequalities. So therefore, I have to give the affine function here. This affine function is defined in this way. So U is element M. So linear part is actually, defined by certain vector in the dual space, and this is Vj. And in this case, actually, this one is not just an element in the dual space, but this one actually lies in the, so this one is Mr and Nr. So this is the pairing of the dual vector spaces, but this one is actually lies in this N. So it's the integral point. And this lambda j is just a constant term, and so this may be certain real number here. Okay. And then this Vj and this form picture are related as follows. So in particular, here are some one-dimensional cones, right? So you have a one-dimensional cones spanned by integral vector. So one-dimensional cones, and then this one is actually spanned by primitive vector. So this is actually correspond to the certain primitive vector. Correspond to this one-dimensional cones, and this one is actually this V1, Vn. So I consider all collection of one-dimensional cones in the fund, and then take its primitive generator, and then call them V1 to Vm. And this V1 to Vm appear here, like V1 to Vm. Okay? So this is the way. I think this is correct. What else can I say? Yes, and in fact, this toric manifold can be obtained as a symplectic reduction, and so I may also remember this. So okay, so here I have this n is this space. Okay, so maybe I have to write here n. Continuous homomorphism from S1 to torus, and n is a continuous homomorphism from torus to S1, and maybe later I also identify it with the first homology of the torus. Right? So you have a one-parameter family, one-parameter subgroup, and then the image actually gives you a one-dimensional cycle, and this one is also isomorphic to the cohomology, first cohomology of this, just to prove back the generator of the first cohomology S1 by this, and then you have here. And so this way you can also see their duality. And okay, so this is n. Okay, so here I have n. And so here I said that this top dimensional members actually spanned by something, and all of them appear as primitive vectors spanning the one-dimensional cones. So therefore, here we have Gn, and then here I have, I don't know, this is just a kernel, but this kernel is here, right? And so here actually we have a standard generators, and so I just denote by this epsilon j. This is kind of standard generators. Then this one is mapped to this Vj. So Vj is actually these primitive vectors, and then they actually span the whole thing. So therefore, this is this. Okay. And then the dual of this is, so okay, so then here I have nr, and here rm, and kr, like this. And then I take a dual of this, then here you have m, and then here is a Gm dual, and here you have K dual, like this, and here you have this MR, and here you have RM dual going to K dual, like this. Okay. So now we consider the space like Cm, and then consider standard action here. Then the momentum map of this thing is equal to 1/2 of the sum, like j square, and j runs from 1 to n. Sorry. No, not sum. So like this. So this is a momentum map. And so, yes. So now maybe I just denote by this map J, P, and this also JR, but J, P, and P star, J star, P star, J star. And then if you consider this subgroup corresponding to this K, so maybe I just denote by TK. And then the moment map for this action is, so if maybe I have to give a name for this. So the momentum map, I don't know, maybe phi of this G. Yeah. So this momentum map is just this, right? Okay. So now I denote by Z. It's actually a this one, so just a level set. And over there, after this TK acts, and then we can get X, which is actually Z over TK. This is symplectic Hamiltonian reaction. So actually, you can get some space by this. So you have to check that this one, is a submanifold, and also this one acts freely or something. But under certain assumption, you can just do this. And yes. So here I have a polytope P here. So P is actually here. P is actually here, right? Inside of here. And here we also have something. Maybe I just. So this one I want to keep. So maybe this one is already okay. So here I have M1. Here I have this R dual goes to this KR dual going to 0 here. Okay, and so okay. So now I consider some element here. Okay. So okay. So here, if I consider this momentum map, and then this one may be written as follows. So this one is actually, I don't know, maybe W in this Rm star. So that what is the dual base? This epsilon j. Okay. So that is the W and this epsilon j is bigger than or equal to lambda j, right? Sorry. So this is the image of the momentum of this one. So actually Cm, the momentum map has image here, and then this is the image of the momentum map, right? So this is the image of phi. And if you consider the point so that it actually killed by this J star. So let's consider the W. So maybe I did not write this delta, and then take delta so that J star W is equal to 0. So just consider such a thing. And then that is nothing but this, right? So you take an image of phi and then consider the zero set of this. So this. If W is a phi of Z, and then I'm considering the inverse image of this one. But this one is equivalent to say that, because this is the exact sequence, if something is killed by this, and then something comes from here, right? So there exists some U, so that W is written as a P star of this U. Okay, and then look at this condition, like W and this epsilon j is bigger than lambda j. But this one is certainly W is this way, so P star of U and epsilon j, right? So W is an element in the dual space, so this is actually in M side, and epsilon j is in N side, right? Sorry. This one is no. This one is in this other. Sorry. Anyway, so you can see this, and then because this one is equal to U and P lower star of this. Sorry. P of EJ, right? But this is nothing but U and VJ. So what you get is somehow this inequality. So finally, this one gives you this U of Bj minus lambda j is positive, right? So namely, this one is actually, I switched these two positions, but this one is exactly this Lj of U. So therefore, what I can say is the following. So you have this image of this momentum map of this Cm, and then consider the loci which killed by this J star, and then such a thing is actually exactly the image of the convex point of P, right? So what I can say is this. So P star of this point of P is equal to the W in the image is phi of Cm, so that J star W is equal to 0. And P is surjective, so therefore this is injective. So this is injective. So therefore you have such a standard polyhedral cone, and then you just consider certain affine subspace, given by this J star inverse 0, and then cut this thing by this affine thing. And then what you get is actually the image of P. So in this way, actually, you can recover this polytope inside of here. And so therefore, if you consider the momentum map of this torus action, and then the image of the momentum map is exactly equal to P. So in this way, actually, we can get some space so that the torus action on X has a moment polytope, which is exactly this P. Okay, so this way actually you can get it. I don't know. So this is just a little bit, quick. But maybe if you know everything, then certainly probably my explanation is not so good, but yeah, I just correct something which I need. Okay. So I think I have another 10 minutes. Okay. So and then since I have to use something later, so therefore I may just remember the following. So the cohomology, ordinary cohomology of so this one, certainly there may be several ways to understand this, but there is one nice description. So I just give you the result. So if X is this compact toric manifold, and then correspond to some fun here, and then if you consider cohomology of X, maybe integral coefficient may be also okay, but today I only need complex coefficient, so therefore I just write this C Z1 dot Gm and modulo so-called linear relation ideal and Stanley Reisner relation ideal, and then consider ideal generated by this. So I just tell you what is linear relation and what Stanley Reisner. Okay. So linear relation is somehow relation among the cohomology classes in degree 2. So okay, so maybe this one is not so nice. Okay, so maybe I just do this here. Okay, so now I have following. So X is a complex toric manifold, and then here I have a moment map to P, which is actually in the real star. Okay, and then take point U from the interior. So to take P from the interior of the polytope, and then consider the inverse image of U at this, by this map pi. And this one we call torus, Lagrangian torus fiber. But anyway, I have such a thing. And then I consider following exact sequence. So just ordinary homology or cohomology. So maybe I consider H2 of X going to H2 of X and Lu. Maybe I consider integral coefficient. And then going to H1 of Lu. And certainly you may have a map from H1 to X, but this one is after a zero map. Maybe later I may do this. And also here, this one maybe come from H2 of Lu, but this one is also zero map. So I have a short exact sequence. And this guy, this one, is actually torus. Maybe this one is actually just a torus orbit. So therefore, this is actually a torus. It's an image of the torus action. I mean, the orbit, torus orbit. So therefore, if you pick one point here, then you have identification of this torus with this guy. Right? And so this is a torus. And then, as I said, the first homological torus is identified with n. So therefore, this one is identified with n. And this one is, we can also see that this one is actually z to the power m. Maybe later I may also discuss this. And so, and then we have this map. And in fact, this one is same as, I already erased, so it's so bad. So this one is exactly same as this map. So we have this map, right? And then actually, so we have a standard delta EJ, and then this going to this VJ. So we have such a map. Maybe I can tell you later. And then you have a kernel of this, and here you have such a map, and then the kernel is actually identified. So this K is actually this. And so if you consider dual of this, right, like this. And so therefore this K star is so. And here also we have this is actually H2 of X, and here is H2 of XLU, and this one is H1 of LU, like this. So we can just identify this. And so we want to understand the cohomology of this toric manifold, and first we consider second cohomology of this. Then certainly this one is isomorphic to this Gm star modulo this image of M, right? And so this is somehow this linear relation ideal. So what does it mean? So I have Z1 to Zm. So Z1 to Zm actually is generator here. So this one, this. So Z1 to Zm, they actually are generator of these things. And then, so yes, Z1 to Zm, yes, Z1 to Zm. And yeah, so here we have M, right? And so we have this. So yes. So now I pick one basis. Okay. So here I pick a basis like E1 En. So this is the basis of the cohomology here, and then here I have basis E1 star En star. And then I want to understand, so this one is actually what I just P star, right? So we want to consider I want to consider something coming from P star E1, P star En, right? Yes, spanned by this in the second cohomology, right? So second cohomology of X is isomorphic to to maybe better to write z1 plus zn, and then by this. Okay. But so now I just write this map, right? So this epsilon j going to this vj, and then I just write it as a vij of e I star or something. So here I have vij. So here this map is represented by the matrix vij, and then this is a dual of that, right? So therefore we have this one is actually the sum of vij zj, and j runs from 1 to m, and I is from 1 to m. Okay? Yes. So this is a linear relation. So linear relation is actually written as follows: vij and zj is equal to 0, j after sum 1 to m, and I is from 1 to m. So this is linear relation, and then Stanley-Reisner relation is given by the following way. So people say this P is a so-called primitive collection. So maybe this one is actually from this VI1 to the VIP. This is a primitive collection. So VI1 that is the VIP does not span member of does not span the member of the fund, but the strict subset, any strict subset spans a member of a fund. So as I said in fund picture, each fund is actually spanned by certain primitive vectors, and so V1 to Vm are all one-dimensional generator of the one-dimensional cones, and then consider collection of such primitive vectors, and then consider the condition that the span of them is a member of the fund we started from. And such a collection is called primitive collection if the whole thing doesn't span a member of the fund, but any strict subset actually span a member of the fund. Okay? And then this is a Stanley-Reisner relation. Namely, this Z1 to Zm somehow corresponds to so-called the principal toric divisor, and this condition says that the corresponding primitive toric divisors common intersection is actually empty. So they are second cohomology class, whose Poincare dual is represented by a certain component toric divisors. And then if the intersection of these toric divisors are empty, then certainly their intersection product is certainly 0, right? So therefore, yeah, you have these things. So these two relations actually holds. And Z1 to Zm are certainly a second cohomology class of the toric manifold. So therefore, we have a map from here to here, right? So Z1 to Zm are second cohomology element here. And they satisfy these two relations. So therefore, we have a map from here to here. The statement says that this is actually isomorphism. And so this is actually the description of the cohomology of the compact toric manifold. And when we consider quantum cohomology, somehow this part must be somehow modified. And in the Fano case, so-called Fano toric variety case, manifold case, in that case, actually, we can keep this linear relation, and then we just deform standardized relation, and then we get this isomorphism quantum cohomology with something like this. And if it is non-Fano, and then this description no longer true, in fact. But yeah, still we have a variant of this, so therefore variation of this. So therefore, yeah, it is not really, yeah, exactly this, but there is some other things. In fact, okay, maybe I just stop here and then I continue after 2 o'clock or something.
因为我自己搞清楚，那他现在说是那个都是